Here is part 2 of our intermolecular forces problem set. And so what we're doing here is now trying some practice problems. And we're just going to go through how these work. So if you were able to come to the in-person where you were able to use the models, this is where you can kind of pick up. So in the following pairs of molecules, which one of the molecules in the pair would have the lower boiling point? Okay, let's talk about this. Lower boiling point. If we have a low boiling point, that tells us we have very weak or less attractive forces. Or intermolecular forces, however you want to think about that. Okay, so we're looking for the one that's going to have the weakest forces. So CH4 or H2O. So the way that I kind of think about this is I want to characterize these. CH4 is carbons and hydrogens. That's non-polar. So the only kind of forces it can have are London. Water, on the other hand, is polar and can have hydrogen bonding. So I want to know which one is the lower boiling point. Well, CH4 is a lower boiling point because it has the weaker forces. London forces are much weaker than hydrogen bonding. Remember, we had this list. Where did we put this list? We had the list of intermolecular forces. And I can't seem, I've forgotten where we are. Oh, here. So here are our weakest to strongest. So if you need that little reminder, right there is good. Okay. So B, NH3 or CO2. And remember, try these before you watch. So I'm going to look at NH3 and I'm going to go, oh, that one's polar. And you might have to review and go back and draw your molecules to know which one's polar and which one's not. But you need to go back and review that. So we have hydrogens that are bonded to, remember, to have hydrogen bondings, you have to have a hydrogen bonded to nitrogen, oxygen, or fluorine. No fun. Okay, so do we have a hydrogen bonded to a nitrogen, oxygen, or fluorine? If the answer is yes, it's a hydrogen bond. If the answer is no, then it is just a dipole-dipole. But here I have hydrogen bonded to a nitrogen. So that is hydrogen bonding. Then carbon dioxide, when you go in and you draw this, right, you're going to have a linear molecule like this, whereas NH3 was not, because NH3 has this lone pair that takes up more space and pushes those hydrogens down. Carbon dioxide is linear, on the other hand, and even though you have these polar bonds where oxygen's more electronegative, it cancels each other out, and so there's no overall dipole moment. Whereas with nitrogen, the dipole arrows of the bonds look like this, and so my overall dipole moment of nitrogen is going to look like this. So NH3 is a polar molecule, CO2 is non-polar, and so you'd only have London forces. Okay, so which one's weaker? CO2 with its London forces. All right, so we have two molecules. They both have a carbonyl, or oxygen double bonded to a carbon. So what else is different? Well, in this molecule, we have CH3. In this molecule, we have a hydroxyl. I want you to automatically think, oh, hydroxyl. What can I do? I can do hydrogen bonding. So if you have a hydroxyl, by default, your molecule is going to be polar and you're going to have hydrogen bonding. So you can automatically do that. Now, in this molecule, you can have hydrogen bonding. This is an acceptor, this is an acceptor, this is a donor. But then you also have two more acceptor sites. So you can do quite a bit of hydrogen bonding with this molecule. So this molecule is polar and we have hydrogen bonding occurring. Let's look at our other one. Oh, over here, we have these acceptor sites, but do we have donor sites? No, there's no hydrogen bonded to an electronegative atom. So we can't actually have hydrogen bonding occurring. So while the molecule is polar, because this is a polar bond right there. So yes, it's polar, but it is only dipole-dipole interactions. So which one is weaker? The weaker one is the dipole-dipole. Okay, CH3COOH and CH3OO minus. All right, so now what are we going to do here? Well, we know that one of these oxygens here is carrying a negative charge, and then this oxygen is in a polar, because COO minus means, well, let me just draw it over here. COO minus means that we have a carbon in a carbonyl and a carbon bonded to an oxygen carrying a negative charge, right? So then it's just a CH3 there. So that's what our molecule looks like here. Our molecule over here is the same thing, a carbonyl, but instead of being a negatively charged oxygen, it's a hydroxyl. So that's CH3 there. Okay, so my question is, what can actually happen here? And this oxygen does have two lone pairs. So this one has a hydroxyl, so this one can undergo hydrogen bonding. It's polar, and it can undergo hydrogen bonding. Our second molecule is polar, but what else does it have? So here, this oxygen here will make the molecule polar, but so does this one. So now we kind of need to look at, can it hydrogen bond? It doesn't have a donor, but what does it have? It has a negative charge over here. So if this negative charge on one molecule interacts with another molecule's carbonyl, carbon, and then it's oxygen and CH3, okay? So this interaction can happen where you have a negative charge and something polar. What do we call that? We call that ion dipole. So what's weaker, hydrogen bonding or ion dipole? Hydrogen bonding, definitely weaker. All right, now, which one of the, in the following pairs, which one would have the lower boiling point? So remember, lower boiling point means weaker interactions. Okay, so let's look here. Again, when you see this hydroxyl, I automatically want you to say polar. I automatically want you to say hydrogen bonding. Now, there might be an additional stronger force that you have to look at, but you can do that. But you should automatically think, well, it has hydrogen bonding. Okay, now this molecule, we have an oxygen in the middle. And so basically what you have is similar to water, where you have the CH2 and the CH3 here, and the CH2 and the CH3, right? It still kind of looks like water, so it's still polar. So this is polar because we have these polar bonds here, and you have an overall dipole like that. So it is polar. So what kind of interaction can we have? Can we have hydrogen bonding? There's no hydrogens directly attached to the oxygen, so no. The only thing we can have is dipole-dipole. So what is weaker, hydrogen bonding or dipole-dipole? And the answer is dipole-dipole. Let's look at the next one. Here we have a nitrogen, and so basically you have to kind of remember this is actually not drawn particularly well, but this shape actually looks like this. And so do you have a polar nitrogen? Yeah, you do have a polar nitrogen, but do you have any hydrogens directly attached to your nitrogen? No. So it is polar, but it can only undergo dipole-dipole. CH3NH2 is a nitrogen, same nitrogen, but instead of having carbon groups, CH3, 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 instead of having carbon groups attached to it, it has one carbon group, CH3, and then it has hydrogens. So each of these is a polar bond. And so this does make the molecule polar. But here's the great thing. We have hydrogens attached to an electronegative nitrogen. So this makes it hydrogen bonding. So which one is weaker and would therefore have the lower boiling point? That would be our first one. Okay. Here I can automatically see that this is carbons and hydrogens. This is non-polar. So therefore I have London forces, and that's it. This one, on the other hand, we have a polar bond here. And so that polar bond is going to make this molecule polar. And so the strongest forces here would be our dipole-dipole, because there's no hydrogen bonding. So which one would have the lower boiling point? Oh, the lower boiling point would be this one right here. Okay. Now, ooh, I'm seeing something with a positive and a negative. So this nitrogen right here is carrying this positive charge, and this oxygen is carrying the negative charge. So we have this molecule that has multiple charges all over it. And so what can end up happening is that you can have another molecule that's the nitrogen side here, right, with our hydrogens. And that positive is going to interact with the oxygen. And then you have a carbonyl, and then you have, there's CH2. Oh, no, and I went the wrong way. Whoops. Okay, so we have our nitrogen, then we have a carbon, CH2, and then a carbonyl, and then an oxygen, right? But the point is that a negative can associate with the positive. And so what do we say when a negative can associate with a positive? That would be ionic. So this is very polar, very, very polar. So polar, it's carrying a positive and a negative charge. And so if you have both in one molecule and you have a beaker of this molecule, you have lots of these molecules, they can form ionic interactions. Then CH3OH, we know that OH tells us we have something polar, and it can undergo hydrogen bonding. So which one is going to have the lower boiling point? It's going to be this. All right. So what type of attractive force exists between all molecules? This is London forces, or dispersion, however you want to say that. Can a water molecule form a hydrogen bond to acetone? So take a look at acetone. When we look at acetone, acetone has 2 lone pairs on the oxygen. So it's an electronegative oxygen with 2 lone pairs. This means it has, it has 2 acceptor sites. It has no donor sites, but it does have acceptor sites. So if I put in some water here, right, my partially positive water is going to form a hydrogen bond right there. So yes, it can. Yes, it can. Can a water molecule form a hydrogen bond to carbon dioxide? No, no way. CO2 is non-polar, right? So you have to have 2 polar molecules that have at least one of them has at least an acceptor and the other one has at least a donor, right? You can have more, but okay, rank the following compounds in order of decreasing boiling point from highest to lowest and explain your ranking. Okay, so let's kind of think about this. When I want to talk about boiling point, I want to talk about intermolecular forces. So let's classify these as being polar, non-polar, and then what kind of attractive forces they have. So the first one is an ether. Remember, an ether is ROR. That's an ether. Okay. So if I look at my ether, I know that my ether has an oxygen that has 2 lone pairs on it. And so that makes this a polar molecule. It is polar. And that polar molecule can undergo dipole-dipole interactions. There's no hydrogen bond donor site. So if you're in a pure beaker of just this one substance, you can only do dipole-dipole interactions. My next substance has an oxygen with 2 lone pairs, but we have a hydrogen attached to that oxygen. So it is a hydroxyl, or we call this an alcohol. And so this is polar, but it can undergo hydrogen bonding. Okay. My last molecule here is a straight chain alkane, and it is non-polar, and so therefore only has London dispersion forces. So we're going to rank the following compounds in order of decreasing boiling point, from the highest boiling point to the lowest. Well, who's going to give me my highest boiling point? High boiling point is strong. attractive forces. So who's got the strongest attractive forces? That is hydrogen bonding. Then it's dipole-dipole, and then it is London dispersion. All right, I hope that helps.